Good evening, sir.
Good evening. Thanks for joining. Okay. So what we can do, we can wait for a few minutes and then we will start the discussion.
Yes, sir.
I hope you can see my presentation and as well as I'm audible to you.
Yes, sir.
Good. Okay, now I think we can start the discussion. Okay, so welcome uh, to the sixth week discussion session. Um, Topic of today's discussion is discussion on the assignment 6 solutions. So I will be as always I will be talking. I will first write some. I will first write a question and then I will wait for a few minutes for you to think about that on that question and then we will discuss the solution. Okay. So let's start with the question number one. So this assignment is about the path connectedness. Okay, discusses the path connectedness of the space. Um, right. So let me write down the first question. So question number one is that which of the following are path connected subspecies? Which of the following species following are path connected subspecies of R? Okay. So option A, set of all rationals. Option B, set of all irrationals. Option C, compact interval 0, 1. Option D, union of the open intervals um, n2 n plus 1. Okay. So let me write down what do we mean by path connectedness. So let us quickly recall what do we mean by path connectedness. So we say f, which is a map from 0 to 1 to, we say, a continuous function from 0 to 1 to your space x such that f of 0 is a and f of 1 is b, a path joining a and b in x. Okay, so we say a continuous function satisfying this condition, a path joining a and b in x. Okay, and if or given any pair of such points, pair of points x x comma y in x, there is there is a path joining x and y, then x is said to be path connected space. Okay, so this is a quick recall to the definition. Okay, now I will wait for a few minutes for you guys to think about this question, whether it is. Yeah, so I will wait for a few minutes for you guys to think about this question, and let me know the answer. Okay, and then we will discuss the solutions. So today's topic of discussion for those who joined just now is the path connectedness, and I'm just discussing the first question. The first question is on the screen, as well as the definition of path and path connectedness spaces. And I'm giving you a few minutes to think about this question and let me know the your guesses or answers. Okay, and then we will discuss the solutions. Okay, so Thangeshwaran has said that C and D are the guesses. Let's wait for Rudra. Okay, let's see what he has to say, and then we will discuss the solution. Okay, so now we can discuss the solution. So the correct answer is C. C is the only correct answer in this. And now let us first see why A, B, and D are wrong. Okay. So let's start with A. So before starting with anything, let me write a, uh, our result. Okay, so this is from your lectures. from lectures, okay, that a path connected space is a connected space. Okay, so given a path connected space, it will be a connected space. Okay. um, yeah, and the proof is also very simple. So suppose if it is not connected, suppose x is path connected but not connected, so so there is a separation a union b, which is equal to x and whose intersection is empty, right? But since x is path connected for a point x in a, let me take a, for a point a in a and for a point b in b, there exists a path f joining a and b, right? um, yeah, so now this path, now image of this path is connected. Now since image of this path is connected, so this has to be in either of the separated set. So it is either in this, or this image is either in b, right? uh, okay, so this implies, so if we assume that it is the image is in a, then b is also in a, right? So which will further imply that beta is empty and a is whole space x. Okay, so this will basically imply, first of all, that b is also contained in a, but a intersection b is empty. So this implies that b is empty and a is the whole space. All right. So this will say that then x is connected. That means there is no such separation, because in separation b can't be empty set. So x is connected. So this is a small proof of that a connected space is a path connected space is a connected space also. Okay, so we will use this fact. Okay, so we want to use this fact that path connected spaces are connected spaces. Okay, so how do we use this fact? So we will use this fact in a contrapositive way. So we will consider the negation of this sentence, and that negation we will use. So what will be the negation of that? That not connected set, something which is not connected, can't be a path connected. Okay. So if x is not connected, so this implies that x is not path connected, right? So what we have done, we have taken the negation in this way, that x is path connected. We were given, we had x is path connected, which implying that x is connected, and we have taken the negation of this sentence, which will give us that negation of the second statement, implying the negation of the first statement. Okay, So this is the fact that I'm going to use. So if either of the option, so option A is Q, option B is R minus Q, and option D was union of the intervals varying over Z, right? So now if either of the set is not connected, then they can't be path connected. All right. Is this till this point it is fine? Is this argument fine?
Yes, sir.
Good. So we just need to say that A is not connected. So, and we have already seen in the last session. Okay, we already know that Q is not connected. Is not connected. And what was the separation that I gave last time? So I started with the rational. I started with the irrational in the subspace topology on Q, and this basically gives you, in particular, you need to take the intersection with Q. So minus infinity to root 2 intersection with Q. Okay, this set union with root 2 to infinity intersection with Q. This whole side is equal to Q. All right. So this is the separation. Similarly for R minus Q, we had given one separation last time. So it is also not connected. And similarly for D also, which is nothing but the union of intervals. So you can consider this separation, which is minus infinity to n union with n to infinity. Okay, clearly this is a separation of this thing, precisely the intersection with this space in both of the side. I'm writing the subspace topology that needs to be keep in mind, intersection with this union. But this is clearly a separation. Okay, so all these three options are not connected, so they can't be path connected. So A, B, D are not path connected spaces. uh, is this clear? Till this point it is fine.
Yes, sir.
Good. Now option C. Option C is an interval, close interval 0 to 1. Now we need to say that it is path connected, and what kind of path you can give into this. So you need to just come up with a path, and that path can be anything. Okay. So if you take any point A comma B, if you take any if you take points A comma B in this interval, you can define a real line. You can define F to be a line joining AB sitting in this interval. Okay, so how you can define? You can just define Ft to be T times B plus 1 minus time A. Okay, so clearly when F is 0, it is A. When F is 1, it is B. And you can see that this is in the interval 0 comma 1. Okay, this is also easy to see. So this is a well-defined map. It's basically nothing but the line segment joining a point AB in the closed interval. So it is path connected. Okay. Okay. So what we are discussing, for those who joined just now, we are today we are discussing assignment 6 from the Invitation to Topology course. Uh, and I'm discussing a question on path connectedness. Today's topic is path connectedness. So I was discussing this question. Okay, which of the following spaces are path connected subspace of R? And only C is the correct answer, and A, B, D are the wrong answers. Okay. Okay. Good. Any question? Okay. Now let's move on to question number 2. Again, this question is about which of the following spaces are path connected. Option A is open unit ball. Okay, so D. All right. So D is not connected. That's why it is not path connected. And why D is not connected? That is also clear, right? Because it is nothing but the union of intervals. So you can separate, you can find a separation easily. Okay. So that's why it is not connected. Is it clear? Okay, good. Yeah, if there is any other doubt, you guys can write in the chat and I will explain. Um, yeah. So those who just joined, I'm discussing this question number 2, which is about the path connectedness, and I'm writing down this question only. Yeah. So the open unit ball BD. So this just says that centered at origin, centered at origin. This is shorthand notation for 0, comma 0, and 1 is the radius of the ball. D is the matrix in R2. So in this, this D is nothing but the usual matrix. So you don't need to worry about. Okay. B option is the closed ball. So I have already discussed the notation. So in this case, the ball is open, and when I put a bar on top of it, it is a closed ball. Okay, that means the circle, the boundary of the ball is also included in this. Okay, option C is the unit circle. So unit circle we all know. It is the set of all points in R2 such that the length of the vectors is 1. Okay, option D is R2 minus a finitely many points. Okay, where F is a finite set. Again, I will pause for a couple of minutes and I will wait for you guys to think about this question and let me know what you guys guess or what is your answer. Okay. Okay. Yeah. So this time you guys have guessed correctly. ABC are the right answers. Uh, Even D is also correct. Okay. So all of the options are path connected spaces. All of them are correct. Okay. So I will I will not thoroughly prove this thing, but I will give you hints to work on the to fill in the details. Okay. So let us first see. So when I say that all of them are path connected, you need to prove them. So basically, you need to give a path for any pair of points in these spaces. Okay, and that is what I'm going to do. So for example, yeah. So for example, A, the unit ball BD. Um, okay. So let me try drawing this and then all right. So this is the ball that we are looking at. Okay, so let me just unfill it. All right. So now this is a ball centered at origin and it is of radius 1. Now the idea here is to take any 2 points. Okay. And then we need to say that there is a path joining these 2 points. So you can clearly see that this is a convex set. Okay. Discs are convex. Yeah. So we know that discs are convex sets. So what do we mean by that? That given any 2 points, there is a straight line joining these 2 points. That okay, that is which is contained inside the your convex set. So discs are convex, and this time we are working with open unit ball. You can the closed unit balls are also convex. And how do we prove that it is convex? You just need to say that given any 2 points, there exists a straight line joining them. And how do we do that? So you can clearly see that you can join any 2 points by straight line. So you need to first construct the line segment, the equation of the line segment, parameterize the equation of line segment, and then you need to prove that this line segment satisfy the disk condition. Okay, that means what is the disk condition? That its modulus is smaller than equal to 1. That is what you need to do. So it involves two tasks. You need to first come up with the equation of a straight line, and the second is that you need to prove that that straight line, any point on that straight line, is part of this unit ball. In other words, the norm of any point on the straight line satisfy the smaller than equal to 1. Okay. All right. So I will skip one of the tasks. So I will give you the parameterized equation of the line joining them, and then I will leave out the detail for you to fill out that why the norm is going to be smaller than 1. So let's take this point to be A1, A2, and this point to be B1, B2. In short, we write it as A bar and B bar. Okay. So simplest equation that you want to join A to B. So at A it should be, sorry, at B it should be, uh, at 1 it should be at B, and at 0 it should be at A. So that's what the equation will look like uh, to me. And you can further rewrite this equation Okay, and this will be the, and this is an equation from 0 comma 1 to your space to bd 0 bar. Okay, so this is what we are claiming, that this is a path joining this thing, and this is clearly a continuous map. Why? Because you can break this equation into two coordinates. So what are the coordinates? T b1 plus 1 minus t a1. All right, t b2 plus 1 minus t a2. Okay, now each of the coordinate is nothing but a linear function. Okay, and linear function are continuous in nature, so this is a continuous function. It is a coordinate wise continuous, so it is a continuous function. You only need to check that the norm of this is smaller than 1, right? And for that, how do we prove that? So norm of x comma y, any vector, is given to be x square plus y square and square root of it. All right, that's what you need to do. Or you can do one more thing. Yeah, because we don't have norm in this case, we need to just satisfy the this metric condition. So what is the metric condition? That the distance between rt and 0 must be smaller than 1. Yeah, we need to satisfy this condition, not the norm condition. But either way, it turns out to be the same. But we need to just satisfy this condition only. Okay. Yeah. So this is the condition that you need to check for. Okay. So this is where I leave the proof for you guys to do. Okay. The similar thing holds true for BD, where we include the boundary as well. Okay. But in that case, uh, this will happen for points in the interior. This condition we will check for the points in the interior, and for the points, yeah, anyway, we need to check that condition only, right? This is the only condition that we need to check, or it can be either equal to 1. So you just don't worry. So this will be the check for the same equation will work. Okay, let me write it this way. And in B case, you need to check this condition, right? Okay. For C, it is a circle. Okay. So for C, we have a circle to be given. We need to, if we take any 2 points on the circle, okay. So circle can also be parameterized. So a circle can be parameterized by this equation. Mm, 0 to 2 pi, you can take this interval 0 to 2 pi, and you can parameterize the circle by mapping it to cos t comma sin t. Okay, so this parameterizes circle. And since this parameterizes circle, and this is a continuous map, right? So you only need to say that you need to use this fact that image of a path connected is continuous image of path connected space is path connected. All right, continuous image of path connected space is path connected. You need to use this fact to say that the image of this interval, now we already know that interval is a connected uh, it's a path connected space, so image of this will also be path connected. So image of this, which is s1, is path connected. Okay, so we use this fact, the image of the continuous image of path connected space is path connected. Okay, now what is left is D. Yes, sphere will also be path connected in R3. Yes. Yeah. So when because you have mentioned sphere, so now uh, yeah, I want to just say that you can use the path connectedness of circle to prove that the spheres are also path connected. Okay. There is only one observation you need to make, that given any 2 points on the sphere, you can find out a great circle passing. So you can find out a circle which is passing through origin and joining these 2 points. Okay. In other words, given any 2 points on the sphere, you can find out a circle centered at origin passing through these 2 points. And now, since the circle is connected, so the circle is path connected, so these 2 points will also be path connected in this sphere as well. So it is, yeah. So that's the proof of that part as well. But it is interesting that, like, that is the one of the proof of the path connectedness of the sphere. Good. Okay. Thanks for notice. Nice you notice. Notice that. Okay. Now D option is R minus finite set of points. Okay, R2 minus finite set of points. So if you draw that R2 minus finite set of points, so this is your R2. Okay, and you have some finitely many points that is being, no, that are not part of your R2 now. So if you take 2 points, let's say X, so take 2 points, X bar, Y bar in R2. Okay, so let's say these points are here. This is your X bar, this is your Y bar. Now you can join them by a straight line. In R2, you can join any 2 points by a straight line, right? It is clear. But it may happen that this straight line may passes through one of the points from the finite set. So let's say your finite set has A1 up to AN, many points. Okay. Suppose this line passes through A1. Okay. So you find out a point. So what do? You bypass this point. And how do you bypass? You break this line into two lines. So you find out another point, okay, which is not A1. You find out you find out other point which is not A1. Let's say you call that point to be X1 bar. Okay. And then you join this with, you join X bar with X1 and then X bar with Y bar. Okay. So now this is your new path connecting X bar to Y bar. Okay. It is nothing but composition of two continuous path, and it is, we can use gluing lemma to prove that uh, it is connected. Yeah, we can use the gluing lemma to say that the gluing of these two functions is also continuous. And suppose you may hit any other critical point, you may hit um, any other point from this finite set, let's say A2, okay, in either of the line, then again you can repeat this process. You find out another point X2 bar which is not on the line, and then you can again get a new path. Okay, and you can repeat this process until you are get rid of all the finite points in your path. Okay, and this process is finite only because the points that are not part of R2 is finite. Okay, so you can repeat this path and you will get a path joining from X bar to Y bar. All right, so I mentioned something which is called, yes, it will be connected because it is path connected, so it will be connected, right? So can you think of any, can you thought of any separation for R2 minus F? So R2 minus F, can you find out any separation for that? If you are saying that it is not connected, if you think that it is not connected, then you must be having some intuitive idea of the separation, right? So what is the separation that you are thinking of? I just want to know that. It need not to be explicit. It is not connected. Arbitrary union of path connected is connected or not. Path connected spaces are connected. That's what I proved earlier. So if you take arbitrary union of path connected, uh, if you prove, so this statement is, yeah. So arbitrary union of path connected spaces is connected if their intersection, if their intersection is also intersection of all the path components is also is non-empty, then the arbitrary union of path connected spaces is path connected. And once you get path connectedness, path connected implies the connectedness. So then you are done. Okay. So so there are two questions now. So first of all, Rudra, are you comfortable with the answer that I gave?
Yes, sir. Sir, but if we consider f to be 0 and 1, and then we can take u dash to be minus infinity to 0 and v dash to be 1 to infinity. So then
So this
they
is
might be.
R2 we are removing, right? We are not removing from R.
Ah, yes, sir. Yes, sir.
So there is no separation then, right?
Yes, sir. No separation.
Yeah. And because I'm proving that it is path connected, so path connected implies the connectedness. So you will get the connectedness. Okay, coming back to Thangeshwaran's question. So arbitrary union of path connected is connected or not? Okay. So if you have arbitrary union of path components, right? So each alpha j is path connected, right? Now your question is this union is also path connected, right? That is what your question. It is not connected. So let me answer that. So your question is whether it is path connected or not. So it is path connected only if their intersection. So arbitrary union of this is uh, and their intersection is non-empty, then this arbitrary union is path connected given uh, each alpha j, a alpha is path connected. Okay, so this is the theorem. So above does not apply in the first question because their intersection was empty. Okay, so their intersection needs to be non-empty and not just intersection of any two pairwise point. It needs to be intersection of all the components that you are taking. All right. Okay. Okay. Any other question? Okay. First of all, let me clear whether this question number two is it clear to all of you?
Yes, sir.
Okay. Good. Okay.
Sir, but then the concentric circles will also be path connected.
So concentric circles will also be path connected. But when you take concentric circle, aren't you just so what is the concentric circle? Union of concentric circle. That is what you are saying, right? So that will be just R2 only, right? R2 minus 0.
Yes, sir. Yes, sir.
R2 minus 0 is path connected space because it is just removing a finitely point five, just zero singleton zero from your space,
Yes, sir.
right? Okay. Any other question?
No, sir.
Good. Um, okay, let me now come to question number 5, which is more related to the thing that Thangishram just asked. Question number 5. Okay. Let A alpha be an arbitrary collection, of path connected subspaces. Subspaces in a topological space X. Okay. If their intersection is non-empty, then which of the following is true? Okay. So option A, that their union. Okay, let me call their union some. Okay, their union is path connected. Option B, their union is connected. Option C, their intersection is path connected. Option D, their intersection is connected. All right. Okay. So again, I will give you a few minutes to think about this question, and then we will discuss the solution. Okay. So ABCD all is the answer basically for all of you, because there is no separation. Does the collection is connected? If it is connected, then it is path connected. If it is connected, then it is path connected. No, it is not. There are spaces which is connected but not path connected. We will come to that example also. Uh, and Thangeshwaram says all of them is the correct answer. Okay, so both of you says that all of them is correct. Okay, so only option A and B are correct. Um, Option A and B are correct, but option C and D, they are wrong. Okay, only these two are correct. Now let me discuss. Now let me discuss the solution to all of you. Okay, yeah. So now let me first start with the path connectedness. Okay, so what we have given, we have arbitrary collection of A alphas, all right, such that their intersection is non-empty. This is the important part, that their intersection is non-empty. Okay, so now for path connectedness, and let's call x to be, or let's call A to be the union of A alphas. All right, so for path connectedness of A, we need to find a path joining any A, any x, y in your space A. Okay, that's what we need to do. So how do we do that? Now, since, okay, so for given any pair of points x, y, let, now since the intersections of A alpha is non-empty, there exists a z in the intersection. There exists a point z in the intersection. All right, and since it is part of the intersection of over uh, all spaces, all right, so this is equivalent to say that z is in all of A alpha each for each alpha in the index set. Now, since x and y are in A, which is nothing but the union of A alphas, x, suppose x is from some ax and y is from some ay. Okay, let me take a better notation, ai and aj for I and j in capital J. All right, now now because of this fact that az is part of all of alphas, A alphas, z is also in a I and z is also in aj, and we know that ai and aj are path connected. Okay, because we are started with a path collection of path connected subspaces of x, path connected subspace. So there exist, so there exists a path f1 from 0 to 1 to ai, uh, joining x and z. Okay, and f2 from 0 to 1 to aj, joining Z and Y. Okay. Now we define a new path. Now we define f from an interval to a, okay, as follows. Um, so that f of x, sorry, f of t is equal to, or we can just take this thing, 0 to 2. This is all fine. 0 to 1 only we can define, yeah. So yeah, how do we, so for in the half of the interval, it is going to be f1. So it is going to be f1 in 2t, all right, where t is varying from 0 to half, okay, and is going to be f2, for f2 is also going to be 2t. No, it is going to be, yeah, it is going to be 2t minus 1 for t varying between 1 half and 1. Okay. So why I've defined 2t and 2t minus 1? Just because to keep the parameterization intact. So for example, when you are t equal to 0, you will get f1 0. When you are t equal to half, you get 1. So f1 of 1 is z. f2 of, and at half you should get 0. So you will get 0. And f2 of 0 is z. And now by gluing lemma, uh, and f1, um, f1 of t is equal to f2 of t for t in the images of in the intersection of these things, okay. Thus by gluing lemma, you guys must have this looked at this, you must have seen this in your lectures. So by gluing lemma, we get a continuous map f, okay, and then we have f joining x to y in a. Okay, so I know this is quite big. I don't know whether it is a big proof for you guys or not, but it uses in essentially, yeah, it uses this gluing lemma argument over here to prove continuity. It uses some argument to define this map f. It uses the path connectedness over here, where I get f1 and f2, and it uses the non-empty intersection over here to find out such z. So this proof can be broken into four parts. First part, where you use the path, use the non-empty intersection property to find out a common z which is lying in the both path components. And once you get that, you apply the path connectedness of the component of the subspaces to find out the path f1 and f2, joining x to z and z to y. Okay, so this will be, that point is your connecting points between any two arbitrary point, right? So in pictures, if I want to draw that, so let's say this is your space ai, this is your space aj, and this is the intersection space, okay. So this is a common intersection space. This is the intersection of uh, all of a alphas, intersection over all of a alphas, all right. and this is your space, this is your point x, this is your point y, and this is your point z in the intersection. So first you have find out a path joining these two, which is f1, and then you have found out a point path which is joining f2, z to y1, and now you are gluing these two paths, which gluing these two paths, which we are using the gluing lemma, okay, to get a new path from x to y, which is called f. Okay, so this is the pictorial argument. So this picture you should keep in your mind in order while writing the proof argument. Uh, okay, and this is how you can break this proof into four steps. First, finding out a common element, then using the path connectedness of the subspaces, defining defining a map using the gluing lemma, and then using a gluing lemma to prove that it is continuous. Okay. Uh, yeah. So this seems a bit. I don't know whether it is too much, too less. I don't know. So what I will do, I will just wait for a few minutes for you guys to think, and you guys let me know whether this argument makes sense. Do you have any questions on the proof or not? Okay. So if you guys have any question, you let me know. Okay, it seems like you guys are comfortable with the argument that I gave, and you have understood the details. Good for me. Um, so coming back to this question, which we were proving, so we have proved that this is a path connected space, right? The union is path connected space, and once we know that this union is path connected space, we know that it is connected as well. Okay, because path connected implies connectedness, so it is connected also. So these two options are direct. Path connectedness we have proven. Then we use the theorem which says that path connected subspaces are connected subspaces. So from that we can deduce that. Why C and D are not path connected and connected? Why the intersection is not path connected and connected? Let me give you an example. Okay. So intersection of A alpha is not connected. So let me give you example of not connected, and then that example will also work for not path connected, because not path connected spaces are not connected spaces are also not path connected. Okay, so let me give you a pictorial example. Okay, okay, this is fine. So you can see that this circle. So your circle is, let's say, A1, and A2 is the interval, which is 0 comma 1 times sorry, minus 1 comma minus 1 comma 1 times 0. So A2 is your interval, Now you can clearly see that their intersection of A1 and A2 is precisely plus minus 1, uh, precisely plus minus 1 0. Okay, two points. Okay, the intersection is 2 points. Hmm. Yeah. So this is non-empty intersection. So it satisfies the properties of the collection. Okay. But if you consider this intersection, which is plus minus 1 0, this is not a connected subspace of R2. Can anyone of you give me the reason why this these 2 points are not connected subspace of R2?
Sir, there is separation, no? So basically, we are talking about -1 to 0, and we are talking from 0 to 1. So then,
No, no,
there is a
these are not intervals. These are points in R2. Don't
oh,
confuse yourself with these are points to R2. These are not intervals.
okay,
What is
sir.
the intersection of these two things? What is an intersection of the circle and the interval? The intersection of the circle, okay, which is black thing in the drawing, and the interval, which is the red part. What is the intersection? Intersection is precisely these 2 points, this point and this point. Now, what is this point? This point is 1 comma 0. How do you write a point in R2? 1 comma 0. It is not an interval. Okay.
Yes, sir. Sorry, sir.
Similarly, this is also another point minus 1 comma 0. Okay. So these are 2 points. Intersection is consists of 2 points. Now my question is why this 2 point set is not a connected subspace of R2? Yes. Yeah. So you had some argument. You can modify your argument. I understood what you meant earlier, but you can modify your argument with this new input.
Sir, but then if we consider these 2 points, then there is still a path that is the circumference of the circle via which these 2 points are
No, no.
connected. So we,
So no. So when I am saying that intersection, so I'm only looking at this point. I'm only looking at this part. Okay, this I'm considering as a different subspace. It is no more part of A1 or A2. Okay, it is
okay.
a different entity now. Now you want to talk about the topological properties of it, which is connectedness, path connectedness of this thing. So now, is this entity is a connected subspace or not? Now, when we say intersection, so we are only looking at the intersection only. We are not looking at the A1 and A2. Okay, not at it as a part of A1 and A2. We are looking at it as intersection. As an intersection, it is just two singleton points in R2. Now, is it connected? Okay, so let
No,
me.
sir.
It is not, yes. So, do you have any argument for that? So, basically, you need to come up with a separation. Now, what is the separation for you?
Sir, 0, the point 0 itself.
Sorry?
The point 0 itself, like a 0 comma 0, the origin. It is
Mhm.
clearly on that point. It is we have a separation. I don't. I'm very confused. Sorry, sir.
No, no. Okay. Yeah. It's fine. Hmm. So, okay, now let me write it in this way. Um think of it as a finite subset, okay? Finite subset of R2. So, is a finite subset of R2 connected? Okay, these two things. This is more general. but this is you can think these two things are same. So now is a finite subset of R2 connected. Now let me phrase this in this way. So whenever I ask you something, whenever there is a question of uh, connectedness of some subspace in R2, you need to ask me back that what is the topology on that, right? What is the topology on that finite subset? So because if in order to talk about the connectedness, you need some topology on that subset, right? So first point is topology on this finite subset F. Topology on F. Now, what is the topology on any subset of any topological space? It is the subspace topology, right? So F has subspace topology from R2. Okay. Now, so this set also, this singleton plus minus 1 0. So this, I don't know why it is confusing, but it is, shouldn't be. Yeah. So these 2 points in R2 also has discrete topology. Sorry, these 2 points also has subspace topology from R2. All right. And under that subspace topology, what are the open sets? Since it is finite subset only, so any finite subset has what topology? It may have different topology, but from the subspace topology, you will only get discrete topology, right? So this has discrete topology. That means each singleton, yeah. So each singleton is an open set in itself, and then this whole space. Just I'm just writing down the discrete topology on this space, which is the union. They have the empty intersection, so this will be the topology on this set. Is it clear?
Yes, sir.
So this will be topology on this set. Now, this is the whole space X. This is the empty set. Now these are the two open set. Now what will be the separation of this set? In order to say that it is connected, you need to find out a separation. Now what is the separation of this set? This separation is nothing but U1. So this separation is nothing but this open set, which is singleton this, union with this open set, which is singleton that. So U1 union U2. And it is clearly, and what is the intersection of U1 U2? It is empty. So it is a separation. Hence, it is not connected. So not connected. Okay. So it is not connected space. So the intersection of a circle and the interval minus 1 to 1, close interval minus 1 to 1 is not connected. Okay. Is this clear?
Yes, sir.
I hope so. It is clear to all of you. I don't know how to say it more simpler. Uh, so since it is not connected, it is also not path connected. Okay, by the result that we have seen earlier. So that means option C and D are wrong. Option A and B are the only correct answers. Okay, so yeah, so let me ask you this then. Do you guys have any other question or any question that whatever I just discussed? If there are any question, we can discuss that. If there are no more questions, we can stop today's discussion at this point. Um,
Sir, I have a basic doubt from a few lectures ago.
okay.
Here in algebra and group theory, we study isomorphism, and in topology, we study
Homeomorphism.
homeomorphism. So,
Right.
is what is the relation of, like, are there any differences between the two?
No, no, no. It is there is no relation. So, so when you have groups, we talk about isomorphisms. And what does isomorphism say? Isomorphism say that two groups. So how do you say when you have sets? Let's say, okay. So when you have sets, then how do you say that two sets have the same number of elements, or they are considering two sets A and B is same thing? When do we say that? When there is a bijection, right? If if there is a bijection, then we say that two sets are same. So we
Yes,
don't
sir.
study set. So we study sets only which are not. Yeah, in set theory we don't study sets which are not. Sorry, in set theory we are only interested in studying set which are not bijective to each other. Okay. Uh, okay, which are different set. We want to study different objects. Okay, so that's why bijection is one way to eliminate things which are same. Okay, similarly in groups also, we want to study different groups. Okay, we don't want to study a same type of group, right? So, but what is the tool to distinguish these two things? So the tool to distinguish that two groups are same or not, we have a isomorphism. We have a concept of isomorphism, okay, which is nothing but a bijection plus satisfying the group properties. It's also satisfy the group properties. Okay, so we want to study groups which are different in nature, and how do we do that? We make sure that they are not isomorphic. Then we say that two groups are different. Okay, is this clear? Now similarly on topology also, in topological spaces, we talk about homeomorphisms. Can you prove Monkr's book proof of the topological sine curve is connected but not path connected? Okay. So in topological spaces, we have homeomorphism, which distinguish given two topological spaces. Okay. So you can have two topological spaces, and we want to study different objects in mathematics. So homeomorphism is a tool to distinguish two topological spaces, where to say that when two topological spaces are same, when they are not same. So that's meaning of same is homeomorphism in topology. Meaning of same is isomorphism in group. Okay, so in that way they are analogous in nature, but they are not related in some sense. Okay, am I making sense to you?
Yes, sir.
Okay, good. So Thangeshwaran asked me about the sine curve to prove that whether the sine curve is closed or not. So let me quickly write down the definition of sine curve. So sine curve is a graph of sine 1 over x function where x is positive. So we consider a closure. Okay, we consider a closure. Now a closure is what? A closure is a union with the limit points of a. Okay. Now, if I draw the graph of the sine 1 over x, what do I get? So I'm not gonna do a very good job in drawing this, but let me Try that. Okay. So sine 1 over x. So we know that when x, sorry, yeah. So you understand the function sine 1 over x. So when your x tends to 0, okay, when your x is tending towards 0, you are attaining higher values. So 1 over x is tending to infinity. Okay, when x tends to 0, 1 over x tends to infinity. So that means you are covering in a small, by moving very small towards 0, you are covering a lot of integers, lot of integers. Okay, lot of large positive integers. You are covering a lot of large positive integers on your way. Okay, and sine function depends on the value of sine function depends on how many times it is going up and down. So it is periodic function. So it kind of depends how many integers you have passed through. So basically, as you move towards infinity, as you move towards 0, you will attain infinity. You will attain maximum and minimum multiple times, and it goes rapidly. So you can't even distinguish the sine curves as you attain 0. You can't distinguish the maximum and minimum in the sine curve. So how will it look like? It will look like straight lines. Okay, it will be that close. Okay, and then it slowly, you can see the graph coming out. Okay, now let me draw this thing. Okay, so this is the sine 1 over x graph. Okay, so this is the graph. Yeah, so this is the graph of sine 1 over x. All right. Yeah, and when I consider the closure, okay, that means you can see that this part. So this part is what? This is minus 1. This, what is the coordinate of this? This is minus 0, minus 1. This is 0, 1. And this is 0, comma 0. So this part is also included because in the closure. So a closure, right? So a closure is precisely a union with 0 times minus 1 to 1. Basically this red part. Okay, so this is the red part and a is the black part in the above graph. Okay, so is this clear? What is the, how does the a closure look like? And now when I say connectedness and path connectedness. So for path connectedness, I want a path joining two things. Now, why does this includes the red part is included? Because you can find out a limit point. You can clearly say that this limit point is converging to this point. Similarly, this limit point is also converging to this point on the y-axis. But it is not part of the sine graph. Okay, but it's not part of the graph. The y-axis is not part of the graph, but it is attained at infinity. These points are attained at infinity. Okay, so this whole interval on this axis is attained at infinity. In so there are sequences which converges to that, but this is not part of the sine graph. So we know that sine 1 over x sine 1 over x is path connected. Okay, why? Because you can, it is a continuous image of a connected set, so it is path connected. And what is the image of it? Is basically the image of R. r positive to r2. Okay, so it is basically going x going to x comma sine 1 over x. So it is image of a connected set, so it is connected. There is no doubt in that. Okay, but the A closure is not path connected because you can't find out any path joining a point on the y-axis, which is on the interval on the y-axis, and a point on the sine curve. So it is not path connected. Okay, you need to visualize this thought. Uh, yeah, but it is connected because whatever. So in the open set, whatever open set you are going to take, yeah, it is connected because if A is connected, which is true because A is path connected. A is path connected. This implies that A is connected. So when A is connected, A closure is also connected. So A closure is connected, but A bar, but A closure is not path connected, but A closure is not path connected. Okay, because you can't find out a path on the interval on y-axis and on the graph. Okay, is this clear?
Yes, sir.
Okay, good. Okay, guys, thank you all for joining. I hope to see you next week as well. And I hope there is no more questions. So let's stop
Sir,
today's
one
session.
more.
Yeah, please.
Sorry, sir, one more question, sir.
No,
Sir,
no,
this
fine, that's
was
fine.
asked. Sir,
Mm-hmm.
this question was asked in an exam, sir, but I was unable to do it.
Mm-hmm.
I'm sending you the Google Drive link where I've uploaded the question.
Okay.
Since we don't know what compactness is, I have doubts in option B and D for this question. Or
Which
question number
question?
six.
Which question are you referring to?
Question number six.
Question
X
six.
geometry. Yes, sir.
Okay, so it is a supremum metric valued function on the interval with the supremum distance. All right, on the closed interval. Okay. So f set of all functions whose image is, oh, it's not connected because it's either in this set or this set. So because it's a continuous function, its image needs to be in either of the set. That is fine now. Now y is compact. Set of all functions whose image is this. X and y are connected. Z is not compact. So obviously it looks like Z is not. Oh, okay. Z is path connected. Yeah, I think so. D is not correct. By just looking at the question, Z is not compact. It is yeah. So because it's Y is X and Y are connected. X and Y are connected. Mm,
Sir, X will be connected because it is a continuous function.
no, no. X is a set of all continuous functions. So you need to come up with a. You need to say that there is no separation in that, or you need to prove that it is path connected, which is simpler in this case. You need to come up with a path on of continuous functions sitting inside that, um, and y is compact. It's compact. That can be true. Okay, so I will think about this question. We can discuss this once we have discussed compactness and all, or maybe next week I will try to discuss the solution of this question. Okay.
Okay, sir. Yes.
Yeah. Anything else?
No, sir. Thank you, sir.
Okay. Good. See you all next week. Bye, everyone.
Bye, sir. Thank you, sir.
No problem.